So in this second video, we will see about the matter waves. So in this matter waves, the introduction part, the nature of the particle, that is wave nature of the particle for in the matter waves. So here the wave is considered as a, that can be specified by a frequency, wavelength and also amplitude, then intensity, like that. It can be spread out and occupies a relatively large region of space. So for the classical physics, it is treated as a particles and waves as a different titles, but in the quantum theory, it can be considered as a dual nature of this radiation. So from this, the wave particles is dually of radiation and the concept of wave nature of this matter. So let us see the wave matters one by one here. First one, de Broglie wave. So he explained about there is symmetry in nature. So de Broglie suggested that light can act as a particle at sometimes, and it also the material particles like electrons can also act as a waves at other sometimes. So this is a suggestion of this de Broglie wave. According to him, all the matter particles like electrons, protons and also neutrons, so in motions they are associated with the wave formation. So that these waves are considered as a de Broglie waves or matter waves. So that is the suggestion of the de Broglie. So de Broglie first explained about the wavelength, that is called the de Broglie wavelength. So wavelength means generally we consider as a lambda. So he explained about from the general formula, that is the momentum of the photon of frequency is given by P is equal to h nu by c. So that is also you know very well because of Einstein's explanation. He explained about the particle nature. So P is equal to h nu by c. So generally we have to take that value as h divided by lambda. You know that c is equal to nu lambda. So that is the value here, and nu by c is also considered as a 1 by lambda. So since you know that c is equal to nu lambda, the wavelength of the photon in terms of the momentum is, so now you have to relate the three values. P is equal to h by lambda, or lambda is equal to h by p here. So what is meant by p? P is equal to mv or mc. So what is mean that m is also considered as a mass and v is also the velocity. Here this is the wavelength of the matter waves. That is, this is called the de Broglie wavelength because this equation relates the wave character and also the particle character. So here the wave character can be considered as, so that is the mass, and is also the velocity can be considered. So that is also called the wave character. So lambda is equal to h by p or h by mv. So that is considered as a de Broglie wavelength. And the next one, de Broglie wavelength of electrons. So here let m is the mass of the electron. So that can be accelerated through the potential difference of v volt. So the kinetic energy can be produced. Thus electron is given by, so half mv square is equal to ev. So because here what happens, potential difference in electron volt, that is ev, and the kinetic energy can be acquired by the electrons, that can be half mv square. So we have to, according to the law of conservative, so it can be equal to both the values. So half mv square is equal to ev. So therefore you have to find out the v value here. So therefore the speed of v of the electron is given by, so v value, v square is equal to ev by, that is m. Here the 2 can be considered as 2 ev by m. So v is equal to root of 2 ev by m. So hence this is the de Broglie wavelength of electron. Next you have to substitute this v value in the above general equation, that is lambda is equal to h by mv. So instead of v you have to substitute the velocity of the electron, then finally you will get h by root of 2 emv. So and also substituting all the constant values. So lambda is equal to, h is the Planck's constant and 2 is the constant, E is the mass of the charge of the electron, and m is the mass of the electron. Then voltage is a potential difference that we don't know about that. So all the simplified values, then finally you will get 12.27 into 10 to the power minus 10 divided by root of V. So meters, or it may be 10 to the power minus 10 is a Armstrong value. So lambda is equal to 12.27 divided by root V. So this is the value here. The next topic is Davison German experiment. So in this experiment, so the matter waves was experimentally explained by this experiment. So in this demonstration, the electron beam, so this is the experimental setup arrangement of this Davison German experiment. So in this case, the electron beams are diffracted and they fall on a crystalline solids. So that is nickel crystals. So it can be get diffracted for matter waves. So the electron waves incident on a crystals, it can be diffracted. So that can be in a certain angle, that is in the certain specific directions only it can be diffracted. So it is also depending upon the varying of the intensity of the incident light. So let us see this. So the filament F is also heated by the low tension battery. So here the electrons can be ejected from the hot filaments by thermoionic emission here. So these acylated electrons, due to the potential difference between the filament and the filament, and also the anode aluminum cylinder is also present by the high tension battery. So this electron beam is columnated by using a thin aluminum diaphragm, and it can be passes through to allowed to strike on a single crystal of nickel. So in this nickel, it can be the electrons can be get diffracted, and it also first it can be get scattered by the nickel atoms in different directions, and finally it can be detected by the electron, that is electron detector. So that can also measure the intensity of the scattered electron beam. So this detector is capable of rotation in the plane of the paper, and it can be denote the angle theta between the incident beam and also the scattered beam. So this incident intensity of this scattered beam is measured as a function of the angle theta. So this is a graph between the theta and also the intensity of the different electron beams. So this graphical representation represents the intensity of the scattered electron with the angle theta for oscillating voltage of 54 volt. So at that point, the given oscillating voltage, so that is the scattered wave shows a peak or maximum angle. So that is in the 50 degree to the incident electron beam. So this peak intensity is attributed to the constructive interference of electrons. So by this constructive interference diffracted from various atomic layers of the target material, so we have to calculate the wavelength also. So because of V is equal to 54 volt from this equation, then you have to substitute in the above equation. Already we found that lambda is equal to 12.27 divided by root of volt is equal to 12.27 divided by root 54. So finally you will get lambda is equal to 1.67 angstrom. So this is the value of theoretical value, and experimental value is also same, that is 1.65, that is the experimental value. So this values agrees with the experimentally and also theoretically observed the wavelength of 1.65. So this is the experiment directly verifies the de Broglie hypothesis of the wave nature of the, that is moving electrons or moving particles. Then the next topic is electron microscope. So this is the picture of this electron microscope that can be given in your book. So it acts as the principle of the direct application of the wave nature of particles. So this wave nature of this electrons is used in the construction of this microscope. So that is called electron microscope here. So the resolving power of this microscope is inversely proportional to the wavelength of the radiation. So wavelength of this radiation, and also the higher resolving power can be obtained by the waves of shorter wavelengths. So according to the de Broglie's wavelength of electrons, so the visible light being used in optical microscopes. Because of as the result of this, the microscopes employing de Broglie waves of electrons and also get the higher resolving power than the optical microscope. So this electron microscope giving the magnification value more than 2 lakh times the common in research laboratories. So it can be the resolving power of that is a more than the 2 lakh times of this common research laboratory. So that is a very accurate object working. In this working, it works under the construction and working of this electron microscope that is also similar to the optical microscope. This is the experimental that is the lens arrangement inside the electron microscope. So here the light source, that is electron source, is present there. So and also the condenser lens is there. In between the condenser lens and also the objective lens, the object is placed between that in nearby the objective lens, and it can be get magnified, and it will reach on the intermediate image that can be reached on the projector lens. In this projector lens, it can be able to magnify that image at almost times of 2 lakh times, and we will get on the photographic plate that is called the screen here. So this is the experimental arrangement of this electron microscope. So that will get the magnified image that can be obtained on the screen. These electron microscopes are being used in almost all branches of science here. The next topic is X-ray. So in this X-ray, so in this topic also, this quantum theory of radiation, it is also explains the photoelectric effect. So when the electrons are emitted due to the incident of photons of energy that can be transferred from the photons to the electrons. So this means the X-rays can be produced here. So first discovery of X-rays. So Roentgen discovered this X-rays because of fast moving electrons come and hit on a target material that can be highly penetrating radiation is emitted. So that radiation is considered as the X-rays. So these X-rays are electromagnetic waves of short wavelength ranging from 0.1 to 100 Armstrong. So they travel along a straight line, and the velocity of light is not affected by electric and magnetic field. So these photons are highly energetic. So this is the picture of production of X-rays. X-rays are produced by this tube. So that is called the Coolidge Tube, and it is essentially a discharge tube. So and a tungsten filament F is heated by an incandescent, that is by a battery. So as a result of this, electrons are ejected from it by the thermionic emission method. So these electrons are accelerated to high speeds by the voltage applied between the filament and also the anode. So the target materials like tungsten or molybdenum are embedded in the face of a solid copper anode. So it can be faced by the target. It can be inclined at the angle of 45 degree with respect to the electron beam. So X-rays can leave the tube through this side. So when the fast moving electrons strike the target, what happens? The deaccelerated suddenly lose the kinetic energy. As a result, the X-rays can be produced. So this kinetic energy of the embedding electrons gets converted into heat, and the targets may be high melting point, and also it has a cooling systems is usually used in this purpose. So here this X-rays can be considered as a two types, that is this X-ray spectra can be considered as a two types, that is continuous spectrum and also characteristics spectrum. So X-ray spectra can be considered as a two types, that is continuous and characteristics X-ray spectra. So in this continuous X-ray spectra, the energy level from higher to lower level, that is from energy the electrons can be go and hit the nucleus of the target, so it can be knocked out the electrons. So that is a ordinary process that is called the continuous spectra. So the photon of energy can be released, that is called the h nu. So this is the continuous spectra. And also the characteristic spectra, what happens, so the lot of the shell levels are there. So because of this shell levels, it can be the fast moving electrons can be go and hit any level of the electrons, that is m, l and m and n levels. So it can be originates peak values at that. So it cannot be goes through the continuous form, that is in the higher level to lower level like this. So it can be go and hit any level of the shells of the nucleus. So that can be produce the peak values. So this is the difference between the continuous and also the characteristics value. And the last topic is application of X-ray. X-rays are used in many fields, that is the medical diagnosis and medical therapy and industries, and also for scientific research. For medical diagnosis, X-rays can be passed through the flesh and we have to easily get any fracture on the bone like that. And medical therapy, it can able to kill the diseased tissues and cure the some skin diseases and tumors, etc. And in the industries, X-rays are used to check the flaws or welded joints, so like that. And scientific research, it is important tool to study the structure of the crystal and materials like that. So these are all the applications of this X-rays. So from this topic, so we have to complete this lesson. So next class we have to continue the 9th lesson.